Yo, what's up, guys? Welcome back. Episode 83. I've got a little bit of soda here today. Ooh, I just brushed my teeth. Alright. Yeah, I believe it's episode 83. Yep. We got episode 83 today, and we got a far-fetched today. Let's take a listen to the sound, shall we? Let's take a look.
Check it out. At Planet Fitness, you can get free fitness training.
We're mixing it up.
We're not slowing
About to
down.
turn on my headshot.
I'm checking my form.
55 lifting 70.
You coming?
Save $28 or more when you join for just $1 down, $15 a month. Cancel anytime. Deal.
Ba-dum. 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 How's that sound? Ba-dum. Nice. One more. Ba-dum. There we go. There's our sound of the day. Jump into a few new episodes here. Or a few new problems on episodes. Okay. Take a look. Solving questions with brain power. Take a look at this problem. Okay, you're given a zero index 2D array questions where questions are is equal to points and brain power. The array describes the questions of an exam where you have to process the questions in order, starting from question 0, and make a decision whether to solve or skip each question. Solving each question I will earn you points, but you will be unable to solve each of the next brain power questions. If you skip question I, you get to make the decision on the next question. Okay. If question 0 is solved, you will earn 3 points, but you'll be unable to solve questions 1 and 2. Okay. Right, because we need 4 points to solve this question and 4 points to solve this question. If instead question 0 is skipped and question 1 is solved, you will earn 4 points, but you'll be unable to solve questions 2, question 3. Return the maximum points you can earn for the exam. I'm a little confused here. The array describes questions of an exam. You have to process the questions in order, starting from 0, and make a decision whether to solve or skip each question. Solving question I will earn you points. You'll be unable to solve each of the next brain power questions. If you skip question I, you get to make a decision on the next question. Okay. Maximum points can be earned by solving questions 0 and 3. So question 0, earn 3 points. Will be unable to solve the next 2 questions. Unable to solve questions 1 and 2. Solve question 3, earn 2 points. Total was 5. There is no other way to earn 5 or more points. Okay, so what's the brain power? Is it every 2? Is that what's going on here? Dynamic programming. I think I need to still better understand this problem because I don't really solving questions with brain power. Oh, okay. Okay, so this is the number of questions you must skip. Okay. Okay, I understand, right? So if we take this one, right, we lose 2 questions. So we can't do this one, we can't do this one. Then we can call this one and increment the points, right? When you return the maximum number of points you can earn for the exam. So in this case here, if we start with 1, we can skip this one, 0, we can't do 1. Now we can do 3, right? So we would get 4, right? Can we earn by solving questions 1 and 4, which is 2 plus 7. 2 plus 5, sorry. To earn 7 or more points. Okay. How can we use dynamic programming to decide the most optimal option for each problem? Store for each question. So I'm thinking, right? We have our 2D array. We loop through this, right? We started each different tuple, right? Or whatever you want to call this array, right? We check whether I think we have to start at each one, right, in order to find the question, right? So we started this one, and we go through the array, right? So we get 3, then we can't answer the next 2 questions, then we go here and we store that result, right? Then we start here, right? Get this, loop through, see that we can't actually go any further, right? So we just max is 4 here, right? We go here, can't go any further, our max is 4. We go here, can't go any further, our max is 2, right? So technically, the best way here would be this one here, starting from here. You get 3 plus 2. Same goes for here, right? We start here, we get 1, and we can go here, we get 4, but we can't do the next 3, so that would be our max. Then we go from here, we get 2, right, but I can't do the next 2, so then we go here, so we get 7. We start from here, we get 3, but there's no 3, so we get 3. We start from here, we get 4, can't go any further, we go 5, can't go any further, right? And so we return 7, so that would be our max. So I think that's the way that we want to think about it to solve this, right? But how can we translate that into code? That's the tough part, and I'm not the best with 2D matrices, so 2D. So let's do is equal to the length of questions. Calls is equal to the length of question 0. We want to print. Let's print out rows. Print out columns. Okay, right. How can we use dynamic programming to make this faster? How can we use dynamic programming to decide the most optimal option for each problem? So I assume this brute force way that we're thinking about it here, there's obviously a faster method to do this, right? We store the... We don't really need to use these variables, rows and cols. I don't think. We can go, well, for I in range rows. So also some hints. Now, I don't really know what the DP solution would be. But I think... Not actually doing DFS. Let's call this like function. All right. We want to call a function here. We want to pass our our current value and our questions, right? Our I and questions, right? So we spoke about this before. We check, well, I believe our base case should be if I is out of bounds, right? If I is greater than or equal to the length questions, guess we just want to return 0, right? Otherwise, points brain power is equal to questions I, right? We need some sort of like max or something. I'm trying to think. we can either calculate the question, right? Or we can skip, right? So to skip the question, it's probably the easy one. We would just recall our function, right? So we do call function questions. I think, right? No, not 0. Why are we doing 0? No, I+1 questions. Now how do we calculate the questions is where I'm not really too sure, right? Technically need to do is we need to go, well, calculate is equal to I'm actually very tired. I'm not thinking well. Maybe I might take a nap, call it here, take a nap, come back. Brain power. Obviously, I need some brain power. Brain power plus, we call a function I plus our original I. Then we want to go plus brain power. I know we recall the function do I plus brain power. But I think not brain power, this would be points. Because then this will get back our next one, right? I think. You obviously want to return the max of I don't know. Maybe instead we want to calculate our max like this. Oh, I plus brain power. Then we want questions, right? What's wrong here? What is wrong here? Oh, we're almost correct. The next question should be I plus brain power plus 1 instead of I plus brain power. The problem states that after solving question I, you must. You jump I plus brain. I plus brain power plus 1. Sorry, not here. Because it's 0 indexed, we forgot about that. So I think we were right, we were pretty close. Okay, I don't think this will submit. Yeah. How the hell can we speed this up, man? I have absolutely no idea. I think there's a thing called memorization, how to speed up recursion, because I'm not. Why do I struggle with recursion? Yeah, I'm not sure, man. I'm not sure how to make this faster. Okay, so here they tell us to create a dictionary, right? I'm not sure. Getting rid of questions here. How do we know that this is the max? Understanding the recurrence relation. Oh. I think I understand. Okay, let's see if this passes. Okay. I'll be back. I gotta go to the bathroom, so I'll be back. So yeah, I'll pause this video. We'll be back in a little bit.
Yo, what's up, guys? I'm trying to fix my mic here. So we actually fell asleep for about an hour, as you can probably tell. But we're back. I think we're a little bit more refreshed here now. So, oh man, that's fucking bright. Jeez. Yeah. So I guess while I was sleeping, we have a new question of the day, which we won't look at, but you know, we're gonna go back to our study plan here. What are we gonna do here? You know, maybe we might. Let's just get rid of this maximum level sum of binary tree. We'll do this BFS implementation. As you all know, I love my BFS. Given the root binary tree, the level of its root is 1, the level of its children is 2, and so on. Return the smallest level x such that the sum of all values of those at x is maximal. Oh. Level 1 sum is 1, level 2 sum is 7, level 3 sum is -1, so we return the level of the maximum sum, which is level 2. Okay. I'm thinking here we have a dictionary here. We create our Q, right? So our Q is equal to DQ. We want to pass in our root to begin with. Well, while we have something in our Q, calculate our length. We want to pop our Q, so we do Q dot pop. Q dot pop. So no is equal to Q dot pop left, right? Well, max val is equal to 0, right, for this level. append max val. Right, so we do max val dot append. Max val dot append. No, sorry. Max val also equal to no dot val. If I is equal to the length, so length minus 1, we at last val, right? Then we want to add that last val to our dictionary. So what do you want to post in there? Jeez. Hella gassy, bro. Drink a hot chocolate, man. Made me kind of gassy, bro. My dick. Maybe we need some sort of level here. Level is equal to 0. Level plus or equal to 1. Max val. If no dot right, we want to append q dot append no dot right. Then we want to oh jeez, man, I keep open. This is so disgusting. Sorry, guys. Jeez. I want to return key value of my dot items if value is greater than return val. The key value of my dot items if value is greater than return value. I don't think this is the best way to do it. I think there's a much better way. I don't even know if this will work, to be honest. Okay, it worked. Can't really remember. I think we did this a couple weeks ago. Yeah, I don't really remember how we did it though. Using a dictionary to store the nums is unnecessary because you can track the max sum while traversing. So how do they do it here? Okay. Level sum is equal to 0. We add this to level sum. Then we do, well, max sum is equal to max sum level sum.
we add the level each time, right? Like some, then we can. Why is this not working? Max level is equal to level. Max level. Oh, it's updated before the comparison. Okay. There we go. I was like, that should work, bro. Okay, how did I do it in the other old one, bro? Maybe I did it a little different. Find out max and return second val on the tuple list. Okay. Interesting. Okay, there are entities. Some of them are connected while some are not. If a city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. A province is a group of directly or indirectly connected cities and no other cities outside of the group. You're given n times n matrix is connected with is connected ij is equal to 1. If the RC and the AC is directly connected and is connected ij is equal to 0, otherwise return the total number of provinces. There are n cities. Some of them are connected, while some are not. A province is a group of directly or indirectly connected cities and no other cities outside of the group. So there's 3 separate provinces here. There's 1 province here. I think that's what we're talking about here. Okay. $547. Let's have a look here because I'm not 100% sure at first glance. Obviously, I know it's a DFS problem. It's just kind of this one's a little hard. In terms of the input, adjacency matrix. Let's check our graph problem. And we check, well, if the city is visited. If city is not visited, add to Hashi, add province. We want to call our DFS function DFS city. Well, we have our DFS function here. DFS city. We want to pass in a neighbor in range N. Okay, if is connected, city neighbor is equal to 1. God, can I not spell visited? Let's watch 547 number of promises. The Leetcode. I'm sure Leetcode has a video on this, I would assume.
Hey guys,
Oh man, this is an old
I'm
video.
gonna go through Leetcode 547.
The OG Leetcode video.
Number of provinces. There are n cities, some of them are connected,
Leetcode.
some are
Oh,
not. If a city
jeez, man.
What's your worst assignment horror story?
I had a 10-page paper, and that didn't turn out too well. Just last night, actually, I had to do 20 idea journals.
Hello, so today we are going to do this problem, which is part of Leetcode Daily Challenge. Number of provinces. So what this problem says is we just have n cities, and some of them are connected while others are not. And basically a city is connected directly to another city. So let's say city A is connected to B. If we have this is connected matrix that we get as in the input, if we have the value for A and B equal to 1, okay? And that's basically what we call connected directly. And then there is connected indirectly, just if, let's say, A is connected to B and B is connected to C, then A is also connected to C, but indirectly, okay? That's just the concepts that we have here. And then what we want to return is the total number of provinces. And what do they mean by provinces? Is just a group of cities that are connected. Now it can be either directly, so there is a direct edge, or indirectly, where you go through other cities to get to the other one. So it's just a group of connected cities is called a province, and the goal is to return the total number of provinces. Okay, so that's what we are trying to solve for here. Okay, so let's say we have let's say maybe something like this with 3 connected to 4 and 5, and then we have 6. Then in this case, how many we have? We have 3 provinces. Basically what we are looking for a province is just a set of cities that are connected. These ones are connected, these ones are connected, and these ones are connected. And this concept in graph is just like a connected component. Okay. Now how do we usually do connected components? You can either use DFS, or you could use union find. You could also use BFS if you want. But in our case here, we'll just use DFS. And the way you do DFS to get the connected component is just like, you start from, we know the number of nodes, so let's say n. We'll just go through each node, okay, and see if we haven't visited yet. So we'll keep track of a visited set. If we haven't visited a node yet, then we'll start a traversal from that node, and we'll keep going until we reach all the connected nodes to it. And so, for example, in this case, let's say if we start from 1, we'll just visit 2, and we will be done, and we'll increment our count by 1, because we just started a visit from a non-visited node and went to all the connected ones. And so here we will add 1 and 2 to our visited set, and we'll say we have 1 more. And then we'll go to 2, but we'll find that 2 is already visited, so we skip it. And then we'll go to 3, because remember, we'll go from 1 to n. And n in our case here is 6. And so we'll go to 3. 3 is not visited yet, so we'll start traversal from 3. And we'll go to all the nodes connected to 3, so we'll go to 4 and then to 5. And so we'll add those to our visited set. 3, 4, 5. And now we'll increment our count by 1, because we just did a DFS, right? And then we'll go back to our loop. We did only 3, and so we'll check, did we visit 4 yet? Yes, so we'll skip it. Did we visit 5 yet? Yes, so we skip it. And now we go to 6. We haven't visited 6 yet, so we'll start the DFS from 6. And we'll increment our count by 3, because we just started another DFS. And then we'll add 6 to our visited set, but there is nothing connected, and so we stop, and we reach the last n, and we stop. Okay, so that's sort of the idea. Basically, we keep a track of a visited set, and we'll try to start a DFS from each node. If the node was already visited, that means it is part of another connected component that we already traversed, and so we just skip it. If not, it means we haven't visited yet, so we start a component from that node. And we'll keep going basically like that until the end. So that's the core idea here. Now let's just code it up and make sure it passes. Okay, so let's code this up quickly here. So what we first want to get the number of nodes, which is so that we can check them. And we have this is connected that tells us whether a node is connected or not. And we are told that this is n by n, so the length is going to be n, which is the number of nodes. And the nodes we have are just the range from 0 to n, okay? In the example I gave, we went from 1 all the way to n plus 1, all the way to n, sorry. But in this case, we can just go from n0 to n minus 1. And that makes the numbering nicer, because here we have connected from I to j. That is easier to do. If you prefer, you could do 1 to n, but then when you are trying to access is connected, you'll just need to do I minus 1 So that works as well. But in this case, we want to keep track also of a visited set, like we mentioned in the overview. And here, if I is not in visited, so we haven't visited it yet, then we want to start the DFS. But we also want to keep track of all the components, and so let's call them components here. And here, because we started from this I, and we visit all the connected nodes from it, this is a connected component, a new connected components. And so we need to increment by 1. And then at the end, we will return the number of connected components. Now we need to write our DFS. So it visits a node I. And when we visit a node, we want to add it to our visited set, and then we want to go through the neighbors. So how do we get neighbors? Well, this is connected, right? So I and j are connected if the is connected I and j is equal to 1. And so how do we get the connected nodes to I here? Well, let's just go through all the nodes and just check which ones give us this, because that's the ones that are connected to I, okay? So this is what's called the adjacency matrix, right? Where the value would be some value if they are connected and another value if they are not connected. There is also, you could if you choose before starting with DFS, just create your own adjacency list, which basically would be node as the key and then the list of neighbors as the value. So you could do that and do the conversion, but since it's easy to do with just this adjacency matrix, let's just do that. And so we'll just try all of them here, and we'll check if is connected at I and j is equal to 1. That means basically that j is connected. Basically there is an edge I to j, okay, if this is equal to 1. But we also don't want to visit something that we already visited, right? So here we want to make sure that it's not visited, so that we don't keep going in circles. And now, so we go through all of them, we see if they are connected. If they are, then we want to traverse this node j, because we want to cover all the connected ones to I here, okay? And then that's pretty much it, right? So we will mark all the ones that are connected to I and add them to this visited set. So next time we won't start the components from these. We will only start components from nodes that we haven't visited yet. And yeah, that's pretty much it. So this one will go through the connected component, and this one will calculate each connected component separately. So let's run this. Let's submit. And this passes, okay? Now, in terms of type complexity, usually for DFS, it's O of E plus V. So what are the number of edges?
I want to run through the test case, man. I just find this stuff so hard to visualize, you know, like. Okay. Let's try and code the PFS version, right? For city in range and sorry, fast, right? So we do while Q. Q is equal to one. Little one. is connected. No, J, what? A J not visited. Oh, what do we do?
We would add it to visited. Append to our queue, right? Man, can I not spell visited? Swear to God. I'm sick and tired of me. Concurrency. Whoops. Let's tag with graphs, dude. And then we can difficulty. We can sort it by acceptance, right? Is this a graph problem, dude? No way. Yeah, that's what I thought. Find the town judge. Let's do a easy problem. Find it. Wait, let's do. Find the center of star graph. Undirected star graph is no level. It's once in a node. Okay, give me an edge list. I don't feel like this is a real graph problem, bro. Bruh. Because really, we just need to find the duplicate here. Like, oh, jeez. Find the duplicate here, right? So. Edges, right? I'm gonna print I. Let's print edges I.
can I return this? I think we need to just play around with these 2D matrices, man. One, two, two, three, 4, 2. Yeah, 2, 3, 4, 2. 1, 2, 2, 3, 4, 2. Okay, we're gonna use some sort of dictionary, I think, to do this properly, right? I have to play around with it. AV in edges. Let's print A and print B, right? Okay. Okay. Dick A is greater than 1. Dick B is greater than 1. Turn B. I think that should work, right? What is wrong with this? Key error 1. Why did A is greater than 1? Why am I getting key error? I don't know. You can revise magic without initializing them first. What? Oh. Right, because they're not 0. There's a .get method in Python. I just don't remember. Get. We get the key, which is A, otherwise 0. Get. Key, otherwise 0. I believe this should work. Get B0. We're getting null. Why are we getting a null value here? I don't understand why we're returning null. No, we're returning null because we're not even getting any of these statements. That means there's something wrong with this here. Oh, we're not incrementing, right? We need to add 1 every time, bro. That should work. Yes. Candy Crush is warm up. Oh, that was hints. We didn't even look at the hints. Given a directed to the graph with n vertices, no from 0. Okay. Find the smallest set of vertices from which all nodes in the graph are reachable. Oh, okay, we have a directed graph here. Okay. So I think this would be a DFS problem, right? We have a graph problem. Okay. Um. Really, what I'm thinking here is that we kind of loop through this and we check, well, whatever value that we're missing in here is, I think, what we return, right? 0 and 3. Because you can't get to that value like what it said in one of the hints, that does not have any incoming edge, can only be reached by itself. And yeah, with incoming edges can be reached from some other node. We only have to count the number of nodes with 0 incoming edges. How can we count the values of 0 incoming edges, right? So let's print B. It's guaranteed that a unique solution exists. Let's say you return the vertices in any order. So we need some sort of res array, right, to turn our vertices. Okay. I mean, we could technically put it inside of a set, right? She's equal to set. We can put hashy dot add b. Right, we can print out hashy, right? One, two, 4, and 5. And we can do, well, for I in hashy. If I not in hashy, I guess we can do for I in range and sorry, we return our res. I need to pen this, bro. Is there a way that we can do it in one whole loop though? That's the thing. Like hash.add b. In degree 0 times m for edge, and edge is in degree. Okay, so they're using the index value of the thing, right? So they're looping through for edge and edges. They're referencing this array and edge 1. So they're looking at the second value, right? So they're looking at b plus or equal to 1. And then they have their answer right here for I in range n. If in degree I is equal to 0, they append I. I applied topo sort and DFS to solve it. Jesus, man. Can you apply DFS to this problem though? That's the thing. I do not know. Find smallest set of vertices. Can you apply 1557? Can you apply DFS? You can use DFS to traverse the graph, mark the node. What is my solution? Okay. Okay. Let's take a look at our do one more solution, powerful study program. Kind of running low on time here. Been going for about 2 hours now, so let's take a look at a greedy problem because I do want to do a greedy problem. Start smashing through these greedies, bro. We have n chips where the position of the ith chip is position I, right? We have n chips. Okay, we need to move all the chips to the same position in one step. We can change. Interesting problem. With cost 0. Okay, we want to move the chips all to the same position. The minimum cost you need to move all the chips to the same position.
I guess, well, to figure this out, my intuition here is to check in what position we have the most chips, right? Because whatever position we have the most chips in, I feel like will automatically be the fastest way. That's what I'm kind of thinking here. So I guess first thing, step 1, right? Find the index where we have the most chips, right? So I guess we can just do, well, position. I'm just gonna call it max index, but it doesn't have anything to do with it, so we do x index is equal to max position. Is that it? Can we do this in Python? Let's print out max index. Okay, we're printing our max number, not our most frequent number. Okay, how else can we find our most frequent number? We could throw it in a hash map. We can just... max val, max index is equal to ydig 0, right? Key value in mydic, right? The value is greater than max val, then we make max val equal to value, but then we make max index equal to key. And we just want to print our key. Bro, what? Bro, what is going on here? Key value on my dictionary.items. Oh, we're printing our key. Whoops. I want to print our max index. Right. So now we know where to move, right? We move to max index, right? So our step 2, So I think our greedy part of the algorithm is that we need to move them all to 2. So we need a cost variable. Cost is equal to 0. So okay, now we loop through I in range, length, position. If position I is equal to max index, okay, position I does not equal max index, then we need to check the bounds, right? If position I how can we do this? Well, if max index equal to position I max index plus 1 within a distance of 1, then we want to make position I equal to max index I is equal to max index. Else if position I we increment our count by 1. Cost plus equal to 1. Else cost plus equal to 2. Position I equal to max index. We make cost plus equal to 2. I mean, technically we don't really need to do this part here, I feel like. We just turn out cost. I don't think this works. I definitely think this is wrong. Okay, that's actually a better thing. If max index minus position I is equal to 1, or max index plus position I is equal to 1, then we don't really need to change this, right? We just increase our cost by 1, right, as we loop through. Else our cost is 2. Okay, so obviously this didn't work. Moving a chip from an even position to an odd position costs 1. Okay, so I did it wrong. So we were doing it based on how many chips are in the position, but they're saying here the best way to do it is to count the even or odds.
Oh, position I plus 2. Oh my god, I totally read this problem wrong. Position I plus 2 or position I minus 2 with cost 0. Position I plus 1 or position I minus 1 with cost is equal to 1. It should be 0. How do we get 0? Do we need the abs here? Okay. So that's why we need to focus on odd and evens, right? Because this is our test case that's not passing. Okay. Step 1, we want to calculate calculate odds and evens, right? Is equal to for I in range odd count is equal to the sum 1 for I in position if I percent 2 does not equal 0. Event count, even count. Why do we print out odd count? That's an interesting problem. An interesting greedy solution. But yeah, we're gonna call the video there. I appreciate you guys watching, and I'll see you tomorrow.